Okay. So, okay, let's just begin. They'll come in later. Hello, everyone. Thank you for coming to today's SpaceBeer. Today's lecture or today's presentation is going to be on the electrical power system, and it's going to be presented by me. So let's talk briefly about me. My name is Dominic. I am the team manager of v2.0, and I'm also responsible for the electrical subsystem. I'm studying space applications at v2.0 together with most of my other team members. Currently, I work as a software engineer at Porsche Engineering, so it's work in automotive, not space. So if there are some questions regarding space, I'll try to answer them as best as possible, but just bear in mind that I'm still learning just as you are. Thank you. Everyone does, I think. So yeah, in the past, I've graduated. I did my undergraduates at v2.0 in automation and measurement, so I have quite the background in electronics design. And I've also spent a year on a full-ride scholarship at UNL, at the University of Nebraska-Lincoln in the US, where I've worked on high-power electronics R&D. So let's say powers of around 18 megawatts and up. I've also been part of T-Urban Racing, the Formula team, and I've co-founded a startup, Voltage Solutions, where we focus on battery control solutions, so development of battery management systems for terrestrial solutions, and now we're also expanding into the space industry. So let's also briefly talk about today's agenda. So I would really briefly like to introduce you to the electrical systems altogether. So it's very, very basic. I'll try to make analogies to mechanical subsystems or things that if you haven't heard that much about the physical background of electricity, will hopefully help you understand. Then we'll talk about the actual electrical subsystem and the overview. We'll talk about the different types of power generation. I'll talk about that. Then there's going to be a brief beer break. And after that, we'll talk about energy storage, mostly batteries. Then we'll talk about the regulation of voltages and the different topologies of power buses on satellites, as well as protection of connected devices as well as batteries. We'll have a short beer break after that because it's quite a long point. And then after that, we'll talk about the space environment challenges and the energy balance and power budget analysis of a. Okay, okay, I'll try to be a bit more loud, a bit louder. So, yeah, we'll talk about the power budget analysis for an example mission that we've done in the past as a part of our curriculum. So, let's talk electricity 101. So, if you've never delved into the basics of electronics, so we can talk about electronics that in an analogy that will hopefully help you understand a bit more. So there's three main, let's say, variables in an electrical circuit. That is voltage, that is current, and that is resistance. If we talk about voltage in water, it's, for example, the pressure at which water comes out of the hose. So you can think about voltage in that way. Current is basically how big the hose is, so how big is the diameter, how much water or how much current can actually flow through the hose, and in that analogy, a wire. And then the resistance, may it be a bad hose, may it be some debris in the line. Same can be put into, for example, resistors. That's a quick analogy of the three most important variables. And next, we can look at one of the most important equations. That is that voltage is equal to current times resistance. That's what we use the most in the satellite power analysis. So what is the main point for us is to analyze how much power we gather and how much power we expend or how much power we use on the different subsystems. And we try to balance it as much as possible for optimization of the power budget over the long duration of the mission, and also to optimize and have the mission be successful and all the components to work the way they are supposed to. So you can see a comparison of a basic, let's say, water loop to an electric circuit. So as I said, resistance is the sand in the tube, and also the pump that's can be thought of as a battery, and the current flowing through is the diameter of the actual wire. Same can be said for electric power and energy. A lot of people confuse these two things. So electrical power is measured in watts, and it is a measure of, for example, how much power over time is in a given moment is required to power a device. And that can be thought of as water flowing out of the hose. How much water can be flown out of the hose in an instant. And energy is put in watt hours or megajoules, doesn't matter. It's how much water you can gather in a bucket over a period of time. So capacity of batteries is given in watt hours. We'll talk about that a bit later. And that's how much energy. A battery can be also thought about as a bucket of water, as a bucket of energy. So that's pretty much the basics, the analogy. And next, we'll talk briefly about what the actual EPS means and what it is in a satellite. I'll try to focus this presentation more on the nanosatellites, and those are the satellites that we deal with. So that's 1 kilo to, let's say, 10, 20 kilos around that. So the main objective is to provide a reliable power supply for the different connected subsystems. May it be an attitude stabilization system, may it be the onboard computer, may it be the actual payload. And our goal, or the goal of our subsystem, is to deliver continuous operation of these subsystems and also regulate the energy flowing in from the solar cells in case of nanosatellites, and the energy flowing out of the battery into different things. The main components of EPS are the power generation. We'll talk about that a bit more. So that may be the solar cells, RTGs, and other sources that we are about to, that we can use on a satellite, or not even satellite. It can be a rover, it can be anything in space. And then there's energy storage. It also may be, it mostly is a battery. Then the power regulation, that is DC to DC circuits, switching regulators, linear regulators. We'll talk about that more. And then the actual power distribution. So it's the protection of the connected circuits. It is the regulation of the loads, so we can switch a heater on, heater off, etc. Let's talk more about the power generation. So there are a number of different types. The main type that we are concerned with are the solar panels. So what we do is we gather solar energy from solar flux from the sun, and we convert it into a usable charge that we can then use to power different subsystems. But there's also different alternatives, as it may be, for example, RTG, so radioisotope thermonuclear generators. So they use the decay of a charged particle and convert the heat from that into a usable power. So solar power is, we convert the solar flux, the solar irradiation through solar panels into a usable power. Let's talk briefly about the principle. So the flux of the sun shines on the surface of the solar cell, and that converts the solar flux into the electricity. So the photons from the irradiation transfer their energy, the moving photons transfer their energy into the electrons, which are in the semiconductor which the solar panel is made out of. These electrons are then excited, and excited electrons like to move, and that creates current, which we can use to power our satellite. Currently, SOA means state of the art. So the current best market available solar panels have about 30% efficiency, which means that 70% of the irradiance is not used for power generation and ends up as a waste heat, for example. And to achieve such a high efficiency in terms of solar cells, it's not a high efficiency in terms of other electrical subsystems, which have efficiency of around 96, 98%. But to achieve such a great conversion rate, there's multiple p-n junctions used from different materials, maybe gallium arsenide or other semiconductors together, so they all work the best in some broad or in some narrow band of the sun wavelength. So we combine these semiconductors, and that's how we achieve such an efficiency. In terms of mechanical configuration, these panels are made of semiconductors, therefore they are inherently fragile and they need a support structure. In our case, they are usually mounted on a PCB, which is a printed circuit board, which is basically layers of fiberglass glued together, and they can have electrical circuits printed on them. That's why it's called a printed circuit board. We can use this printed circuit board to take the connection from the semiconductors from the cells and lead it into the EPS system where other things happen, which we'll talk about later. And on the printed circuit board, we can also mount different sensors or different antennas. For example, on the side of the satellite, such as this one, we can use the surface, or this one, we can use the surface to mount a GPS antenna, for example, or some sensor which will tell us how much sunlight the panel sees, and we can then point the panels to a better location to get more power, because the angle at which the solar panel is irradiated is important, because the function is not linear, and we need to be able to, in case of the bigger satellites with folding out solar panels, we need to be able to point them in the right direction. And this configuration, if it's deployable, if it's rigidly mounted, is mission dependent. So the deployable panels, which are much more complex structure, are useful for missions which require a lot of power. And a great example of that can be communication satellites. And probably the best known example is Starlink, which uses a fold-out solar panel, and the solar surface of the solar panel is about 24 meters squared. So it's a really huge solar panel and a pretty big satellite. And also, not only if the satellite needs a lot of power, but also if the satellite is far away from the sun. Because as we look, the solar flux is reduced with the root of the distance of the square of the distance from the actual source. And the rigidly mounted, which is case for our missions, either it be mission Kostka or mission Simmer, is much better in terms of the complexity. We just use the PCBs to hold basically the structure together, and then if we need more power in terms of the mission Simmer, which is a 3U CubeSat, which we've already discussed in the previous lectures, is a pretty long or elongated CubeSat, and there's surfaces which are more profitable, let's say, to point to the sun to get more power. And for that, we need an AOCS system, which is a system that points the satellite into the right direction of the sun. We can look at this short demonstration of fold-out solar array. So this is from Kongsberg Nanoavionics, and as you can see, the solar panels themselves are on a support structure. In this case, it's a honeycomb substructure, and thanks to that, they can fold out. These mechanisms are challenging to test on Earth because engineers tend to over-design these parts because, or during testing, they break, and that case may be because they don't support the solar panels during the testing. So in this case, these fold-out panels need to be supported either from below or from the top, because in the orbit there's no gravity to act on as a pulling surface, as a pulling force on the actual fold-out panels. So that's what needs to be taken into account when designing the mechanical system. In terms of electrical configuration, there's difference between a solar array and difference between a solar cell. So solar cell is a small part. You can think of it as a small battery, and a solar array is made out of these batteries. So these cells can be connected either in series or parallel, or they can be connected in a series parallel configuration, and each has its own advantages and disadvantages. It's also mission dependent. For one new CubeSat, usually the EPS, or the system that takes in the inputs from the solar panel, has enough inputs for each of the panels or each of the faces of the satellite to have an individual channel, and it's not to be influenced by the shading of the satellite. For bigger satellites, that may be a problem, and that's why the bigger satellites use a series and a parallel combination. And it's a balance between the optimization of the voltage from the solar cells and the current that gets outputted from the solar cells, and the impact of shading, either it be from the actual structure of the satellite, so the part of the satellite which does not gather the sunlight can act as a shade on the solar array and can reduce the efficiency greatly. We can look at such an example. So this is the comparison between the series connection and the parallel connection. So it's a comparison between three solar cells where there's always a shade on the one on the left. And in the series connection, we can see that the shaded solar cell limits the current through each of these, for each of the panels, therefore resulting in reduced output power. Instead of the achievable 300 watts from each of the panels, we get only about 157 watts. That's when the panels are connected in series. This is beneficial if there's no shade, because then we reduce the current and increase the voltage, which means there's less losses due to the Ohm's law. And in terms of the parallel connection, they have advantage when one of the panels is shaded. So the voltage of the entire solar array is lower, but the current is not limited through one of the shaded panels. So these two panels can work fully, so they both produce 200 watts, and only this panel is crippled. Whereas here, this panel cripples the entire series connection. And you can see it in the comparison of the output wattage. The shaded panel with the series connection has 157 watts output, and the parallel connection has 255. Let's talk about the energy flux. That's what gives us the power on the solar array. So the sun emits a solar flux, and KO, the flux at the nominal distance of 1 astronomical unit, which is the distance from Earth to sun, is about 1400 watts per meter squared. And that means that at the efficiency of 30%, we can gather around theoretically 400 watts of power. And that, as you can see in this formula, reduces with the square of the distance. So at Mars, even though it's only a half a distance more, it's only 1.5 astronomical units, give or take, the output power of the theoretical solar power we can gather is only 176 watts. So it's much, much lower. And the other example is the planet Jupiter, which is 5.2 astronomical units away. And if someone can calculate the theoretical power together that we can get on Jupiter's orbit or surface with the efficiency taken into account, I'll buy him a beer and a beer break. So who can do this and can come up to me, I'll buy him a beer. Okay, so there's limits of solar power, as is obvious from the previous images. So we can only use solar power, or where it's usable is only up until the Jupiter's surface, where the power is usable enough for it to make sense to use them. So beyond Jupiter, there's the conditions are too poor. For example, at Saturn, we only get 15 watts of solar radiation on the solar panels, as well as the temperature is too low for the solar panels to work properly. So it is a combination of the solar intensity, the temperature, as well as the radiation, because the solar irradiance is not only made out of the wavelengths which the semiconductors are designed together, but also from different radiations. So solar cell performance is influenced by the environment a lot. It is the sun intensity, so it's obvious that the more sun, the more power we can gather, but it's also dependent on the temperature. The curve changes quite a bit. Yep.
So the satellites beyond Jupiter are powered only on the batteries?
No, I'll get to it. That's a good question. I'll get to it after I'll do the solar cell presentation, but it's a good question. So the temperature also influences the power output from the solar cells as well as the radiation. It influences the semiconductor itself, and the cosmic rays can actually damage the different PN junctions and therefore reduce the output power. At the beginning of life, you can see how the curve looks like, and the end of life, the area under the curve is much lower, therefore the theoretical output power of the solar cell is much lower. But it is not just a matter of taking the solar cell or the solar array and connecting it to the battery that would result in suboptimal performance. So what we need to do is to match the impedance of the solar cell to the system that it is connected to, and that's the DC to DC converters are used to that. DC to DC converters take one voltage and convert it to another. Basically, in this case, we use it as a adjustable impedance. Impedance is a resistor, so a hose. We can change the diameter of the hose to limit how much energy can flow through the wire. MPPT algorithms, which you might have heard about in the past, or also quite recently, are used to improve this performance. So it's a maximum power point tracking. So the algorithm to continuously monitor the output current and output voltage of a solar array, and using that, the DC to DC impedance is changed, and that's how we try to track the point to be here. This is where the maximum power point of a solar cell is. So if you would just connect it to a battery, the output voltage or the voltage would be reduced to the battery voltage, and therefore the power would not be optimal. It would be at about here. So we can use such a circuit. It's not a complicated circuit. It's quite simple, and we can use it to almost double the power in an instant just by correct regulation of the solar cell. And there's the alternative. So in case we cannot use solar power, that's beyond Jupiter and also for other deep space missions, we use something called radioisotope thermoelectric generator, which use the Seebeck effect, which is an effect where if there's on a semiconductor, on a thermocouple, if there's two different temperatures on each side, as can be seen here, as the hot side and the cold side, a voltage is generated, or the voltage potential is present on these 2 points, and we can use this voltage as a power generator. So what is used is an isotope with a decay that decays over a long period of time, and that heats up the inner core of the generator, and the outside, due to it being in the deep space, is cooled to an extremely low temperature, and in the space below, in between of them, there's the thermocouples mounted on the sides, and this is what's used for the actual power generations. There's also radiator fins to increase to cool the cool side down even more. These are also used in a terrestrial situation, mostly in the military and defense department, as well as in the Arctic region, where USA is using it for the measurement equipments in the Arctic. And the USSR has used about 1,007 of these generators for uncrewed lighthouses. And in the past, it's quite a bit of a funny story, these generators were not documented properly. So over the time, people lost track of them, and they've been rediscovered by normal people who have no idea about the isotope and what the radiation can do to their body. So they've taken it as they wanted to sell it, and they've basically got a radiation poisoning out of a power source, a radioisotope thermoelectric generator, because the documentation was not sufficient. But as of 2021, it is documented that all of the generators have been recovered successfully, so there's no more danger if you go to Siberia of finding such a generator, probably. Okay, so that's everything for the first part. There's beer time now, and after the break we'll talk about the energy storage. And let's meet at 6:50, if that's okay. Yeah, thank you. So, okay. Jirko, drž hubu. So let's continue. The question was already answered, so thanks to those who paid attention. The answer was 14.8, I think. I don't know who answered it correctly and who got the beer. I don't know. It's okay. Okay, let's continue with energy storage. We'll mainly focus on batteries. I don't know if there are any other energy storage solutions. They don't come to my mind. Maybe a rotation wheels or inertia wheels can be used as energy storage, for example. They are used in Formula 1. That's a different topic. Let's talk about the batteries. So when you have a satellite on orbit, you cannot always have the sun shining at it, mostly. In most types of orbits, or in the orbits which we are interested in and which our satellite will orbit on. So batteries are used to provide an energy source during those eclipses, when the sun is not shining and the satellite still needs to be powered. Either may it be for downlink, so that is downloading the data from the satellite, or it is running an experiment, it is pointing of the aircraft, it is taking pictures, it is doing some other scientific mission, or doing some communication with either other satellites on stuff on the Earth. It still needs to be powered, so in most applications we can't just shut the satellite down. And it also ensures the power bus stability, because there are electronic devices. For example, it may be transmitters, which take a lot of peak power in bursts, where the solar cells may not be sufficient in powering them with these peaks, and we can experience a brownout, or blackout, which is an event where the voltage dips below a certain threshold where the devices power off and are not able to function properly anymore. So the main parameters of batteries are if they are rechargeable or non-rechargeable. There's also the non-rechargeable batteries are used very scarcely, but the most ones that we will be looking at are rechargeable. And these chemistries might be lithium iron phosphate, nickel, cadmium. So it's different combinations of elements which form their chemical properties allow us to store a charge in them. So the other important parameters are the energy capacity, and because the satellite needs, or the rover or the satellite needs to be small and light. An important parameter is also the energy density. But it's not only these parameters which we are looking at for batteries. We'll look into that a bit further. Also, what's important is the current which the battery can input. So it is the charging current and the current which can go from the battery. So how much or at what rate we can discharge the battery. Let's talk about the words or the nomenclature that you can hear when talking about cells or, say, batteries in general. That is capacity. And it is a measure of how much energy a battery can store. There's a certain misconception, or people say things wrong, that the capacity of a battery, when you ask them what's the capacity of a battery on their satellite, they'll say 15 amp hours, which is not wrong, but it does not give you the entire picture because you don't know the voltage of the battery. What tells you more information is if they tell you the battery has 48 watt hours, which means that the battery is able to supply 48 watts for an hour. And that gives you the entire picture and is not dependent on any other variables. So it is better to measure the capacity in watt hours. that makes sense, and that's the unit of energy, and so that's what we use, and that's what's mostly used in the documentation. Next, which is a really important parameter in the space missions, is the depth of discharge, which is you have 100% charge of the battery, and the depth of discharge basically is in percentage how much you discharge the battery and the usual the usual percentage that you aim for these missions which we work on is about 30%, because there's a lot of cycles that the battery goes through over the mission, and if you cycle it more, the capacity of the battery decreases rapidly, and that's detrimental to the success of the mission. State of charge is the remaining charge in the battery. The very simple way of measuring the charge that's left in the battery is just measuring the battery voltage. So a normal lithium polymer cell, which is usually used in these nanosatellites, has a maximum voltage of about 4.2 volts. And the cutoff voltage is around 2.93 volts. So you can use this scale to measure the capacity or the state of charge of the battery. However, this method is not accurate. As you can see, the discharge and the charge curve of these batteries is not linear, so it doesn't give you the entire picture. What's best and what's usually done for this high price and high importance mission is the battery is characterized before, so we have a couple of samples of the battery where we measure discharging at different temperatures, at different discharge rates, and in different conditions of the cell, so how many life cycles it has, and that's what gives us the best picture of the state of charge of the battery. And yeah, the nominal voltage is, for example, for the lithium polymer battery, usually people say we have a 7.2 volt battery on our satellite, but the voltage on the battery is not constant. It fluctuates between, as I said, 3 and 4.2 volts. So that is just the nominal voltage. That is the voltage where the battery is at, let's say, the default state. And an important parameter which is used to simplify things is a C rate. So that is the input and output current, charging and discharging of the battery expressed in a multiple of the capacity in the amp hours. So when I have a 5 amp hour battery and I charge it with 1C, I charge it with 5 amps. If I have 2C, I charge it with 10 amps, etc. So that is basically sort of showing, telling you the performance of the battery without needing to have more parameters such as the battery voltage, the capacity, etc. It just gives you an overview of the chemistry that's used and the quality, let's say, of the cell that's used. Yeah, and as I've said, the battery discharge depends a lot on how you discharge it with what current. So in the top picture you can see 5 different curves. One is discharged with 1C, then it's 10C, 20, 35, and 33 and 35, and that is the multiples of the current. And as you can see, the faster you discharge the battery, the less capacity it has. So the capacity, the energy that's actually stored in the battery, is the area under each of the curves. So this is how much energy is in the battery. So if you discharge it with low currents, you can gather more energy from the battery than if you discharge it with big currents. And in space, there are temperature extremes, so it's high temperatures and low temperatures. And that's shown in the curve below. So if the battery is discharged in a freezing temperature, the energy is much lower, and actually the chemistry in the battery gets damaged quite a bit, and you reduce the number of cycles that the battery can go through. But if you optimize it to, let's say, optimum is around 20 to 40 degrees C, and if you do that, you can gain much more experience, much more energy from the battery, as well as increase the lifetime of the battery. So what we try to do is keep the battery happy, keep it discharging slowly, charge it slowly, and keep it at a okay temperature. And we use that. We use heaters for that in most of the EPS systems. Next, there are many different battery types, and I've also included capacitors in this. So in this graph, you can see how much energy is stored in the battery in the y-axis, and in the x-axis, you can see how much power is stored in the battery. So the conventional capacitors, the small radial things you can see on circuit boards, don't store a lot of energy. However, the small amount of energy that they have, they are able to deliver it quickly. This is useful for when you have a fast circuit that needs to operate quickly. Usually when you have an IC, a processor, there's these small things around it. Those are usually decoupling or capacitors which are used to balance the voltage of the power bus, so that there's no brownouts in the processor. And that is because the wire that goes to the processor has a resistance, so there's, let's say, sand in it. And by using these capacitors, these are basically small tanks of water which we can use to supplement when the input hose cannot supply enough water, and we can use these tanks to supply enough power for these processors. And there's different types of capacitors. There's ultra capacitors, which are a balance between capacitors and batteries. And what's important for this part, the battery storage of the satellite, is the conventional batteries, which there are many different chemistries, and you choose it based on your mission. So if you need a lot of cycles and you don't need that big of energy density, you use a chemistry which is optimized for that. If you need a lot of power and not that many cycles, you use a chemistry that's optimized for that. So there's many different options. In future, the specific energy density is predicted to rise, and the energy that's stored is probably the most energy dense is the lithium cells. So that's the cells which are mostly used now in missions. There's a different chemistry used, for example, on the ISS, but there are plans to improve their batteries as well. Next, let's talk about the battery connections. So there's series connections and parallel connections, and you can combine these to make a series parallel connection. So series connections means you connect the positive of one battery into the negative of the other. And doing this, you take, let's say, for example, four 3 volts batteries, and 4 times 3 is 12 volts. So you will have a 12 volt battery, but the battery capacity will only be the capacity of one of these cells. If you use a parallel connection, that's how you increase the capacity. So you will connect the positive taps of these cells together, and then the negative taps of these cells together. You will have the output voltage of 3 volts, but if you have 4 batteries with 10 amp hours, you will have 40 amp hours. And, but the energy of these two configurations will be the same. It will be the same watt hour, but it is just an optimization for the system and for whatever suits your mission the best. And you can do series parallel combinations. And you can have, for example, 12 cells in series with 4 cells in parallel. So you need, for example, an increase of voltage because your bus is 28 volts and you only have 3.6 volt cells. So you connect a number in series, and then you say, okay, I need more capacity. So you connect these strings, the same strings, in parallel next to each other, and that's how you increase the actual energy that's stored in the batteries. Yeah, that's basically the example that I've talked about now. So the nominal voltage of for example, such a battery is 3.6 volts. The nominal capacity is 2 amp hours. We connect 15 cells in series. We have 15 cells. We connect 3 in series, 5 in parallel. Therefore, the nominal voltage of the battery, not the actual voltage of the battery, will be 10.8 volts, and the nominal capacity will be 10 amp hours. And the energy is just the nominal voltage and the nominal capacity of the battery segment, and the resulting is 108 watt hours. That's the nominal. And you can see how these batteries are made. So this is one cell, and they are connected in such packs. So these tabs are connecting the cells in parallel. So these are all negative tabs, and these are connecting them in series. So the positive tab connecting to the negative tab of the different string, etc. The battery capacity itself is non-linear, and it's also not linear in terms of the mission duration. So at the beginning of life, the capacity of the battery is, let's say, 10 watt hours. It's at this point, but at the end of life, the battery capacity can be about here. You know that from your phones. If you have a phone for 5 years, and you can, after 5 years, you have to carry a power bank next to you at all times because your phone shuts off in an hour. But when you bought your phone, it lasted for an entire day. And these losses are made up of different parts. So that is the worst case cycled energy. So how many cycles of the battery taking into account discharging the entire state of charge of the battery. Then the failure margin of each cell. So you can measure the chemistry, but the chemistry might change a bit during the implementation. The cycling loss and also the calendar loss of the chemistry in the cell itself. The drift in, you have these batteries connected in series, but they are not made exactly the same, and each battery is a bit different. The higher the quality of the battery, the more similar they are, but there can still occur manufacturing errors, and the machines used to manufacture them are not perfect. So there's drift in their battery voltage. It's also caused by the overstress by high loads. So it might be a switching of a heater, for example, for some element or for some scientific mission. It may be the aging of a battery. When the battery has more than 1,000 cycles, the capacity is greatly reduced. And I'll talk about it in the design of the power budget, but such a cycle is also pretty low for our missions. And then it is, what's a key factor is the temperature delta between these cells. So as you can see in the previous picture, the energy of one cell, if you discharge it at -10 degrees, is much, much lower than if you discharge it at 20 degrees. And the temperature in the satellite differs. So that's what also differs in, that's what makes the difference in the battery voltage. And the result is reduction in battery capacity, accelerated degradation of the battery. So the cell that's working well cannot supply energy to the cell that's working poorly. So the entire battery is limited by the bad cell. And that's the usual, that's what is normal with current systems. The entire battery pack is as good as the worst cell in the battery pack. That's when you use a passive balancing system. That's when you just, what you need to do is maintain the same voltage in each of the cells. But if you do so, one cell may just have less energy stored in it. So you cannot increase the voltage in this cell because this cell is capped off here and there's no more room to go. That's when you use passive balancing. There's a method called active cell balancing, which can actually charge the battery artificially higher, which it basically takes the charge from the battery which is more healthy in this case, and it can artificially, over the discharge profile of the battery, transfer the charge into the worst cell and therefore achieving a greater state of charge compared to the passive method. And in that way, it also reduces the heat output of such a balancing system, because if you use passive balancing, you basically, the voltage that would otherwise get used on systems would just get burned up in heat. So the active system takes this energy at an efficiency of, let's say, 95% and transfers it into a different one, into a different cell. And you can gain about 5 to 10% depending on the age of the battery and the quality of the cell itself. Yeah, and for different chemistries, there's different battery discharging curves. So the measurement of the state of charge as a function of the battery voltage was useful, for example, for lead-acid batteries, because as you can see, it's quite linear. It's not perfect, but it is much more linear than such a lithium-ion cell. So you think you have a state of charge 95, 90, 85, 80, and then suddenly it dips below, and you don't expect that. That's why better methods are used for that. Yeah, and yeah, the lithium discharging also, as you can see, the capacity is the area under the curve of such a discharging curve. In the battery charging, you cannot just connect a power supply to a battery and expect, or let's say connect a solar cell to a battery and expect it to charge. There's a certain protocol, a certain methodology that needs to be used in order for the battery to have enough, in order for the battery to accept the energy, and in order for the battery to last long. So we have, this is the charging procedure for a lithium-ion cell, so the cells which are used mostly on a satellite. So what you do at the beginning, the cell voltage is low, so it's about 2.5, 2.8, the cell is discharged. What you do, you connect it to a power supply, and the power supply needs to have a constant current mode, which means the power supply limits the amount of water which can flow into the bucket, and therefore the bucket gets filled up slowly. If you would connect a fire hose into a small plastic bucket, you would just destroy it. So that's why you need to have constant current. And after the bucket fills up, you switch from constant current mode into the constant voltage mode. So you basically just trickle the water into the bucket until it's filled up to the brim. And same is with the battery. The battery has an absorption region, so it still absorbs energy. But then if you disconnect the power supply, it sort of has a memory, so it tends to go a bit slower. So even if the charging current is quite low, you need to maintain a constant voltage, because the battery is still accepting charge, but not as fast as it was before, because there's not enough room for the charge in the battery left. Next, let's talk about the power bus. There's two most used topologies, or the ones that differ the most. That is the unregulated bus. That is the bus that you can see on top. And it's the simplest system. The battery is connected directly on the bus, so you can see there's no system between the battery and the bus. So the bus voltage is exactly the battery voltage, and you take this battery voltage and you connect it to your subsystems, maybe OBC, payload, etc. So as the state of charge of the battery changes, so does the battery. In a regulated bus, the voltage of the bus is finely regulated. That may be for bigger satellites where you need to have the granulation a bit lower, and the systems on the bus are more sensitive to the ripples in power supply, so that's why these are used. And it also simplifies the connection of, simplifies the design of the connected devices, because they have a voltage which they can expect, and they don't have to do anything else with it. They don't have to reduce it, they don't have to increase it, they don't have to do basically anything. And the most common power bus voltages on satellites are, on the bigger ones, or the pretty big ones, is 100 volts, 50 volts, 28 volts, 14 volts, and about 8 volts, which is approximately the nominal voltage of the two cell batteries connected in series. So it's 3.6 times 2 is 7.2, but yeah, the voltage fluctuates up and down. Let's talk about nanosatellite power bus. That is the power bus which will be most likely used on the mission Kostka and also mission Simmer. And it is a combination of a regulated and unregulated bus. So the batteries are connected directly on the bus. So the bus voltage is equal to the battery voltage. However, this voltage is not suitable for all of the components. So the OBC expects 5 volts. So in that case, we need to take the bus voltage here, which is 8 volts, have it go through a component that's called DC to DC converter, which takes the input voltage and converts it down to 3.3 and 5 volts. And that's how the loads are powered. The LCL is a protection of the circuits. I'll talk about it in the future steps, in the future slides. And SARs are the regulators which are responsible for tracking the maximum power point of the solar cell. So it's the solar array regulator. That's where the MPPT algorithm lays. And when you talk about EPS, and for example the AMUN, which is the Spacemanic EPS, which we plan to use, these things are integrated in it. So the solar regulators are included, so you just plug in the solar array directly into the EPS. The battery is part of the EPS, and also the output protection is part of the same circuit, of the same board. The DC to DC regulation is done just to reduce or otherwise work with the voltage to optimize it to a circuit, to the needs of the connected circuit. So let's say an OBC is powered by 3.3 volts and the bus voltage is 12 volts. So we just use a DC to DC converter, which takes the voltage and puts it down. There's different types of DC to DC regulators. I will not talk about all of these. What's mostly used is a switching mode and sometimes linear mode when the power is quite low. But what's mostly used and what's optimized for higher power is switching mode. And in our case, it would be the buck configuration. The three main types of the switching regulator are buck, boost, and buck boost. Buck is a regulator which takes 10 volts and reduces it down. So buck is a converter that reduces voltage. Boost, as the name implies, is a regulator that takes 10 volts and increases it to, let's say, 100 volts. And buck boost is a regulator which is usually used in battery charging. So you can have a voltage range in, let's say, 10 to 20 volts, and the output would be, let's say, 15 volts. So you can take a voltage that's lower and that's higher, and you can have the same output voltage. So it does both boost as well as buck. The main difference between a linear regulator and the switching regulator is concluded in this table. So the linear one is really simple. It's basically just a valve on the hose, and using that, or a divider on the hose, let's say, that's a better point, which directs only a certain amount of voltage into one circuit, in the one that you want to power, and the rest of the energy or the rest of the power is taken into ground as heat, which is not good for high power applications because you want to limit heat generation. It's extremely important in space because heat management is really, really tough, as you'll see later. And the switching one basically has a switching element or a switch which turns it on and off based on how much the connected device needs. And there's a smoothing circuit on the output. So the advantages of the linear one is it's a very simple. You just divert some of the voltage somewhere and burn it as heat or water the garden with it. And the switching one is more complicated because you have to still control the output. The pros of the linear one is the output noise is very low because there's no switching element. The connected circuits can be less disrupted, and it's used for example, when you have an accurate measurement that needs to be taken and you cannot have ripples or waves in the output voltage. And for switching one, it's used when you need a lot of power or a higher power than where you would use a linear one. For the circuit protection, they are usually included in the EPS, however, they don't have to be. They're also sometimes included in the OBCs, so the connected devices, the onboard computer, because the designers of the OBC don't trust the integrator or the manufacturer of the EPS to protect the bus voltage sufficiently. And they can include a protection of, for example, the inrush current or the reversal of the voltage. If you plug plus to minus and minus to plus, bad things can happen, but there's also protection devices which can take care of that. The main types are latching current limiter. So the current that goes into a device is limited on the EPS, and that is because if one of the devices fails, you only want that particular device to fail. You don't want every other device on the same bus to fail. So that's where that is used, and it's used only for, or mostly for non-essential loads. So this protection cannot be re-triggered. So you cannot turn it on and off remotely. That's where resettable latching current limiters are used, and they can be turned on either by a watchdog, which is an algorithm, or let's say a timer that runs in the back, and in case something is not refreshed in a certain period of time, the entire system is reset, and you can use that to reset the output of the channel. And yeah, the watchdog automatically attempts to switch the resettable current limiter on. And this is used for essential loads. So an overcurrent situation may happen on an OBC, but you don't want the OBC to be always off because the mission would be a fail. So the OBC is only shut off for, let's say, a second, and then the circuit comes back alive. And if the overcurrent event is not happening, still, the circuit will work as before the fault. Similar to LCLs, there's fuses, which are also single use. They don't have any reset functions, but they deteriorate quite a bit because the materials which are used in them are, we'll talk about it a bit, used from components of the shelf, so it's automotive parts, etc. And these are not optimized for use in space. So when something is optimized to be used in space, it's usually in a red hard packaging, so radiation hardened, and this is how the packages usually look like. They have sort of a gold appearance. It's usually ceramic packages. And what the LCL looks like, so you have a nominal LCL current, which is the current which is the circuit designed for it to flow through, but in case there's a fault, the LCL needs to trip off at the trip-off current. But there's also inrush current. When you plug a capacitor into the circuit, there's inrush current flowing, so the LCL usually has a time to wait until the inrush current deteriorates or reduces, and if it doesn't reduce in a certain period of time, the circuit shuts off. In practice, this is what an EPS looks like. So we have the actual battery pack. These are the exact same cells that we've looked at before. So there's 4 of them. They are connected to the battery unit, and the battery unit monitors their current, their voltage, and from that, the battery unit is connected into the conditioning unit, and the conditioning unit has 4 switching regulators on it. So it's in inductor capacitors, and this is used to have the different bus voltages, so 5 volts, 3.3, 1.8. And then the distribution unit has the protection on them, so the LCLs. So you can connect your actual devices to it, the OBC, and they will be protected using this part. You can see in the before, this is what the common interface looks like. So usually the nanosatellites integrate a PC104 connector or a standard, and this is a standard that's, it's not really a standard, but it's sort of used a lot in the nanosatellites. And this allows for stackable units. So you can have different OBC, ADC, payload, have the same interface, and they will just connect to each other. And based on your definition of the pinout, they can then communicate. The common interfaces that are on this connector, or also, as you can see here on the example, this connector, which flow through these actual pins, is the power, 3.35 volts, the bus voltage, and then the communication standard. I will not go into the actual communication standards, but the most used are serial UART, RS485, I2C, and CAN bus, and each has its different advantages and disadvantages. And the honorable mentions are Ethernet and SpaceWire, but these are only used, or mostly used, on satellites which are bigger, which have a lot more information and a bigger data rate, so more information needs to be passed through the OBC. And this is what the actual CubeSat components look like when they are connected to each other. So you can see the PC104 standard and then the connector. And the entire stack has no other cables, and they are just connected through this. And they can communicate, they can power, they can do all of it through this. This is what the actual PCB looks like, and this is another stack module. So yeah, thank you for the attention for this part. There's going to be a beer time break, let's say up until 7:40, if that's okay. And then we will just go through energy balance and the influence of space on electronics, and that's it. Thank you. Let's begin with the last section, and that is the section on energy balance and power budgeting and the power budget analysis. So what we will talk about is the energy balance of a low Earth orbit satellite, and the important or the key parameters for us are that the orbit lasts approximately 90 minutes, where we spend 60 minutes in sun and 30 minutes of eclipse. So 30 minutes where our satellite does not see the sunlight and we need to rely on the battery power. This orbit is also the orbit where most of the satellites are launched. I think that Starlink is also launched in low Earth orbit. And the effects of the 90-minute orbits are that it is shorter than day, and per year we have more than 5,000 cycles on a battery. So it is quite important for the cells to be sustainable and for them to maintain their charge over the charge cycles. The solar flux is approximately 1,300 watts per meter squared, and the altitude is lower than 1,000 kilometers. So the energy is very limited because of the solar panel, and that's why we need to consider every component as well as the losses. They play also quite a big role in the design of their power supply. We also have to derate each of these components because the manufacturer gives us a number, and that number is to be taken with a grain of salt because they don't usually give the accurate number. The best thing is to measure the power consumption ourselves, and also the power consumption may not be the same as measured in the lab as well as in the orbit, so it's good to have a margin of, let's say, 10% on top of what we measure. You can say that the efficiency of most of the components is quite high. So the efficiency of the regulators is 98%, the charge efficiency is 98%, the discharge efficiency is 98%, as well as the efficiency of the power distribution unit. But if you take all of these efficiencies together, the resulting best case scenario is only 92% output efficiency. So only in these small inefficiencies, you lose 10% of the entire power of the satellite. And this is for all of the components, either it be the payload or anything else. So what you need to do is maintain a positive, or let's say at least maintainable energy balance, where the state of charge of the battery after each orbit reduces comes to the same percent. If the state of charge of the battery dips as the time passes, it is a poorly designed mission, and it may be sufficient for the mission duration. There may be a need for this in case you're limited with the mass or the space, but this is not sustainable for longer missions. So either the depth of discharge of the actual satellite is too high, so it is, let's say, from 100 to 40, so the depth of discharge is 60%, which greatly reduces the number of cycles that the battery can go through, and the SOC, as you can see, walks down to 0, and after some given period of time, the satellite is no longer usable and will not produce the results that we need. What is a good energy balance is when the depth of discharge is small, so in this case about 20%, and the orbit-to-orbit situation is the same, so it comes down to the same state of charge after each of the orbits, and this is what you want to see after you do the power analysis. So let's go over a power budget example. We did this as a part of the class at the space applications. So the mission was called Simera, where our goal was to have a real-time road imaging of a defined area, where the prime customer was the Ministry of Transport, and our goal was to monitor the state of the highways or roads in our country. We used or the main component was a camera, Multiscape 200 from Simerasense. And this was the main key component that we've built the entire system around. So in the mission definition, as was done with the mission planning, as was done with, within the system engineering, there was decided what components to be used, from which we know that we needed a payload, that's the camera, the stabilization system, the data processing unit, and the comms unit. All of these components are powered with a different voltage branch, as well as they consume a different amount of power. And in the entire modes of the satellite, either it be imaging, either it be science mode, either it be safe mode, nominal, downlink, etc., they are either on or off. And that is shown in this duty cycle. So duty cycle means the percentage of time that the components are on during the mission. We've taken all of these power requirements. First, we've calculated the total power or the worst case power for each of the voltage branches or voltage buses, from which we were able to calculate the total current. And we've picked an EPS, which has some limitations on the output currents. And we could see that these currents are within the limits. What we've had to done in this mission was to move the ODP power from the 28 volts down, or from the 12 volts down to the 5 volt branch, because the power was too high and the voltage of the branch would not be sufficient, and the power, and basically the satellite would not work. So there's compromises which you need to make. So first, you combine the power consumption of all of these devices, then you check the EPS limitations, so the current for each of the buses, and then you calculate the worst case power and the total average power of the satellite per orbit. From that, we have the worst case and average power, where we have also the orbit parameters, so we know how long the period of the orbit is, and we know how much time we spend in the shadow where we don't have any energy coming in, from which we can calculate the capacity that's required for the worst case scenario, but that's not to be taken into account, just to show that we are able to power the satellite, even if the satellite would be in an eclipse for the entirety of the orbit. But most importantly, we were able to calculate the capacity required for the average energy, or the capacity required for the satellite for the orbit. And we've taken that power and we've derated it, because you still need to have margins, because you know the actual components and the actual system, how it will work on the actual orbit. So we know that we need so much energy to be used during one orbit. So from that, we've looked at SatSearch or CubeSat components or whatever manufacturers you have to find the best or the most suitable battery. We've chosen this one, and these are the parameters of the battery. So it has 90 watt hours. As you can see that it's a lot. You only need 24 watt hours, but the battery has a capacity of 90 watt hours. You do this to limit the depth of discharge, so that the battery lasts a long time, because this is not a mission for a year, this is a mission for a couple of years. From that, we were able to calculate the depth of discharge, and we could validate that such a battery can be usable in the system. So we have those components out of the way. So now we know that we can use that battery, the capacity is okay, the voltage is okay for the voltage bus, because the camera is powered by 28, or the AOCS system that which we used is powered by 28 volts, so we needed a 28 volt battery. Where am I? Yeah. And we could then calculate the solar panel requirements, so the average power which is needed to gather over the period where the satellite is in the sun. So we've evaluated the needed average solar power from the orbital parameters and also the parameters of the power. We've checked the available solar panel area, so we know how much space there is to be used on the satellite, so we could then from that evaluate how much potential power we need to gather, from which we were able to choose a solar panel candidate and configuration according to the EPS limitations. Because as you will look at the data sheet of the EPS, there's limitations for how many solar cells can be connected in series, how much current can flow through each of the channels. So you need to take that into account when you're designing a bigger satellite or satellite where you need quite a big bit of power. So we could then calculate the power generation for a chosen satellite or for a chosen solar panel. This is the parameters of the chosen solar panel, and we can see that the power generated was sufficient, that the total surface area, the power generated for the total surface area was okay. We also calculated the open circuit voltage of each of the solar cells, and we can see that it's within the maximum ratings of the EPS, and also the current at the maximum power point, which is 0.5 amps, and the total current input of the EPS is 4 amps. So that's how you basically validate that that the solar panels are sufficient and that the configuration of them is sufficient. If you were to connect them all in series, it would not be a sufficient or a usable configuration, because the total open circuit voltage would be much higher than the allowed input. So you need to make choices in that point, from which we could see that the power budget is good, that the depth of discharge is good, that we maintain the good state of charge over each of the orbits, and everything is nice, and we can call this done. This is done over an iterative process because the power modes change, the duty cycle changes, the mission ConOps changes, so you do this iteratively, and it's best to have either an Excel or some software where you can input these things, and then you can have an output, and you can see if it's okay or not. So just flags and just see where your mission is, and if your mission is feasible. Next, I would like to talk about the influence of space. We are in the LEO orbit, so our satellite is not doesn't see such bad conditions that satellites, for example, on Mars or in the deep space missions see. So we don't have to deal with some particles which are extremely damaging, or some cosmic rays which could damage the solar panels. Yeah, you can see the mission duration for us is quite low. It's only a couple of months, so the pico and nano satellite region, whereas for bigger communication satellites, it can be within years. So there's much bigger probability that that the components on the satellites will get hit by some stray particle. Yeah, you can see that the mission duration is quite low compared to the highest levels of reliability for the medium and large satellites, which get costly because instead of components of the shells and automotive components, you have to use radiation hardened components with some certifications for ones that we don't have to take into account in the nanosatellites. Space is harsh. Space is hard. And there's a couple of reasons why it's hard. So it's the vacuum conditions which impact the heat distribution of the components. So even a small output or even a small loss of power can be detrimental to a component, and it can lead to a fault or overheating of the component. The big issue is also outgassing. Then for temperature extremes, it's the thermal expansion and contraction, because as you rotate on the orbit, you see upwards of 50 degrees Celsius and downwards of, let's say, 30 degrees, minus 30 degrees C. So the entire structure and the components on the PCBs itself expand and contract. And then the vibrations and shocks during launch, as well as radiation and physical damage to the solar cells using the space debris. So let's talk a bit more about vacuum. So vacuum, if you're in vacuum, you cannot easily conduct heat into the atmosphere because there's none, and even small components which are working fine properly on the ground can overheat, and the big risks are also outgassing. So some of the components, as they outgas, they can either depose the gas, the glue or the plastic from the packaging of these components or from the plastics which you use to print, I don't know, some holder, can actually outgas, and it can lay on the optical elements, and you can also damage the camera, and the camera can become unusable. A big thing is also metal whiskers, which are small, really small metal whiskers which grow on the components, and they can form short circuits within the circuits itself, and you cannot see them. And it is a big issue, and also in case you don't use a quality enough manufacturer for the PCBs, you have to, what can happen is the lamination of the PCB itself. So if there's some gap of air that's laminated into the actual structure of the PCB, it can try to, remove itself from the PCB and can damage the tracks and damage the components on, on the board. So for temperature extremes, one extreme is high temperature, so overheating of the components, but the low temperature is also a risk. So you can reduce, you can see before, the battery capacity is greatly reduced as the temperature decreases, and also temperature cycling is a big issue for the fatigue of components. So if you cycle it enough times, the solder joints on the actual components can crack, and it can cause an issue, and the components can disconnect or not have a proper enough connection. This can be cheaply tested. There's TVAC chambers where you can test both the vacuum and the thermal properties of your satellite. So these are the parts which can be quite prevented with correct design. On the bottom left, you can see an actual data from a satellite, from a Czech satellite, and you can see how much the temperature fluctuates. So you can see in the minimum, it's on the z-axis minus 34 degrees C, and the maximum is 50 degrees C. So it's quite high even on the low Earth orbit. Mechanical stress is also a big issue even on the PCBs. Even if it's a small thing, it's a small board, you say that there's no resonance, but during the launch there can be a lot of resonance of these components, and even if it seems that the component is rigidly mounted, it can end up in this way, and the component can wiggle itself away from the board. Shocks are big issues during launch, particularly pyro shocks, but these things can also be tested on vibration and shock mounts in the testing chambers. Radiation is a big issue for bigger satellites, but we'll talk about it a bit as well. Now there's, let's say, two sources of radiation. That's the solar radiation, and then the galactic radiation from the background of the universe. And these particles, or these flows of particles, tend to get trapped in the magnetic field of the Earth in the Van Allen belts, and that's where the big problem lays, and that's where your components can be damaged the most. Radiation has two effects. It's a long-term and a short-term effect, or a single event effect. In the long term, it's called the total ionizing dose, and it is measured in K-rads or in grays. And the effects are shifting of thresholds. So for example, on the bottom right, you can see that over the total dose, the voltage that is required to erase a memory decreases, and it decreases to a point where the memory itself will fail to erase. These can also read in the leakage currents as well as the timing changes on each of the components. So as the gate source voltage changes on the components, so does their timing, and it can lead to unfunctioning processors or other components on the board. This can be partially mitigated by shielding. So you can see Each of these particles can be shielded by some form of shielding, but it is not, you cannot really send a concrete brick into a space and have it be on a satellite and expect it to protect a neutron. That's basically not possible. These things can also be ground tested, but it's more expensive than TVAC tests. And what's kind of bad is single events. That single event effects, these are caused by one really high energy fast particle, and these can damage the actual dye itself. These are caused by heavy ions. There's two different errors which can occur. There's soft errors, which you can reset. That's lead chaps and upsets. And there is hard errors. Oh wait, that's upsets and transients, and hard errors are lead chap and burnout. So hard errors are the bad ones. I mean, both of those are bad, but hard ones are really bad because you cannot reset the computer and have it function the way it was before. So the severity of the fault is dependent on which one of these happens, as well as how critical the system is. In case one of your heater fails, it's not as bad as if you hit the imaging output FPGA of the camera sensor. This can also be mitigated by either error correction, using of watchdog for the soft errors, redundancy voting, and shielding. So what you can do if you don't have enough resources to invest into radiation-hardened FPGAs, you can have a number of these FPGAs on the board and have components of the shelves which are much cheaper and faster, and then you can have a voter on the output, and that is radiation hardened, so you can compare these three outputs and vote, or you do the majority voting and see which one of these, in case one of these fails, you can still mitigate the fault. There's one thing that was kind of interesting for the single events. So there was the Clementine mission, which was launched in 1994. It was a scientific mission, and on one event, the main onboard computer sent out a command which caused the thruster to fire, but this event was sent out unintentionally, and it is thought to be caused by the single event. And by the time this single event was able to be mitigated by the ground control, the thruster has burned through the fuel, and it was spinning so fast that the mission was a fail. So a single bit flip can have no consequences at all. You may not even know that it happened, but if you're unlucky, Clementine failure can happen. So I've talked about components of the shelves and radiation-hardened components. So components of the shelves are the ones which you can go to an GME or Mauser and buy them. And then there's radiation-hardened components, which are much more tested. They are in different packaging. They have higher standards. And the difference between them is that the radiation-hardened components can sustain a much more radiation dose, so TID, total ionizing dose, but they are also much more expensive, and they are less technologically advanced because they take a long time to develop. There's less demand for them, and the lead time is long, so you cannot just go online and order it and have it here within a week. So it's quite a pain, but when you need them, you need them. And a big issue is space debris, micrometeorites, which can also damage the cells. And an example is a Sentinel-1 satellite, which was damaged by a microsatellite, and it caused a rupture in one of the solar cells. And that's why the mitigation is some sort of protection. This meteorite can cause either a short or an open circuit, and this can be mitigated by the use of a diode or stuff in parallel. So in parallel or in series, so you can sustain this fault and have this satellite still be functioning, even if one of the cells is done, is not functioning anymore. So there's a lot I talked about today. I hope it was useful for you. But there's also a lot of things I haven't talked about yet. So that's the OBCs, ADCS, the different regulation algorithms, The transmitter has different stuff regarding EPS. If you're interested in this, if it's something you would like to be a part of, you can become a member of VSpace, and you can also become a member of EPS subsystem. And with that, I would like to end. And I would like to say that space is hard, as you could see, but if it was easy, everyone would do it. Thank you. If you have any questions, I'm happy to answer them, and we can maybe grab a beer and you can come up to me and we can talk about it. Thank you.